about machine learning on the edge for robotics application. You might have heard the buzzword of AI everywhere, and in this session we are going to look for its benefits and its drawbacks and disadvantages and challenges for robotics applications, basically. I forgot the clicker. Cool. First of all, about myself, I'm working in a new product innovation team at Dyson. What we do at MPI team, we basically look for the future generation of the products at Dyson. You know our range of products. We have purifiers, vacuum cleaners, lights, hair products that are very popular these days. Headphones, I don't know if you've heard of them. We do headphones now. And robots, which our team is very focused on these days. So role of MPI team is to look for the next category of the products and also next generation of the products. So the things we are designing right now is going to be released for 3 to 5 years, just to set the context. So here is a quick video about the latest robot we have released a few months ago, just to set the context, and then I'm going to explain each specific challenge for dealing with AI and processing on the edge.
When Dyson engineers created the robot with the power of a Dyson vacuum, they designed pioneering new technology, like this Dyson hyperdymium motor, creating powerful suction. Then they added a full-width motorized brush bar, Dyson's first with 3 ways to clean across all floor types, so it deep cleans your home properly. A piezo sensor monitors dust levels over 15,000 times a second, adjusting power for more suction when needed. Other sensors detect a wall and automatically activate an extending side duct to direct suction to the side, providing effective cleaning right to the edge. While Dyson's advanced dual-link suspension maintains traction and balance, climbing up to 21 millimeters while retaining consistent wheel downforce so it avoids getting stuck. A D-shaped body makes cleaning into corners easier. And its 360-degree vision system sees precisely where it needs to clean, analyzing up to 10,000 data points a second, mapping and navigating intelligently. Equally smart is the My Dyson app, so you can control cleans wherever you are. Only a Dyson works like a Dyson. Buy direct from the people who made it.
Thanks for watching that video. So some of the challenges of this robot is due to its vision system. Basically, generally in household robotics, you have the scenes changing a lot, and people normally move their furniture, kids playing with the toys, and things always changing. So the robot normally uses the vision system to localize itself and map the environment. Now, how do we do that in a classical algorithm reliably? And also think about, if you pick up the robot, put it somewhere else, you still want to localize the robot. So that's about the vision system. How about changing the light? Therefore, at night, we have these ring of lights that they come up, so you can see the environment. You have bumping sensors in front, long-range sensors to avoid hitting the obstacles, and filtering, battery, and all different challenges of robotics that you all need to put, different teams need to work together and put it in that single product. Now, normally in robotics, the localization is one of the challenges I talked about. Perception, when you want to perceive the environment, what is in front of you, if you can allow it to move it, if you can hit it or not hit it, is it delicate? Is it a staircase you're going to fall or not? These are all categorized as perception. Navigation, basically in robotics, moving from A to B without hitting any obstacles. And Again, consider that inside the home, everything will change. And even the floor is not constant. You have carpet, you have fluffy floors, you have little level change that your robot needs to go there. And also think about it. If you're going on a level change, all your sensor values are moving up and down. So how do we deal with this? I'm just introducing all the challenges in classical robotics that AI could potentially solve those. Manipulation. This is one of the projects my colleagues done in research team, how to help robotics, how robotics can help you even automate further things and open up and free up your time at home. If you can wash dishes or pile up a stack of the dishes to the dishwasher. Human-robot interaction is another challenge. What is the best way of humans interacting with the robot? Is it through the app? Is it through the robot itself? And is it through voice commands? Do you want to talk to the robot? So a lot of research lies in there and a lot of innovation there. As you can see, it's a very active market. And control systems. If you want to, let's say, vacuum your sofa, you first need to scan the sofa, take the shape of it out, and you have a detailed maneuver to go through the arm of the chair there to clean it everywhere. And you know, people wouldn't buy robots if they don't do a good job. So you have to actually provide the value to the customers. So AI normally tends to be more adaptive to the changes. That's one of the benefits that it brings to the table. And it's better in uncertainties. If you wrote an algorithm in a classic way to deal with this sort of environment, and your pet walks in suddenly, everything changes there. You don't know how to perceive that. Is that a chair leg that you need to clean around it, or is it like a pet? So these are all complex things that is so many complexities to be able to type in a traditional programming manner. Personalization is another thing that AI could bring to the household robots. Your robot could learn your behaviors and your patterns and your lifestyle and change its behavior to that. And we're not talking about just the vacuum cleaning the surface. It's automating your whole house environments. And continuous learning. Each person's personality is different, and the robot will learn from them continuously as you use it. Next time and next time, you will just do better for yourself. So these are all the things AI can bring to the table. So what are the main ways that you could put AI into robots? The very famous one is supervised learning, basically, or you can call it teacher-student, that you have a big data set of labeled data and you just run through them, and the neural network will learn from those labeled data to repeat doing what you were doing. So you have a teacher, inputs and outputs, and in robotics, it will translate in if I do something and I tell the robot just to look at me and do it, or I move the robot in a certain way and ask the robot to repeat the same maneuvers, basically. Unsupervised learning is used to let the agent or the robot to discover its own patterns on its own. This normally is being used in classical machine learning as classification challenges. You give a bunch of images and it will just find and classify them in different groups. And it is being also used in robotics, but not as much as reinforcement learning. This category is very big for robots because you can design an agent and drop it in an environment and it will learn by interacting with the environment. So this is the big difference. You have an environment, you have an input to the agent and output, and it will just interact with the environment and learn. So if you design a robot that is supposed to go from here to there without hitting the wall, you don't code it specifically to the robot and say, wheels forward, stop, whatever, no commands. You just design the reward function. This is the key. And you say, for example, when you get closer to that point or when you arrive there, you get a reward, like a human body that receives dopamine from the things that we do and we perceive it well. and you receive a punishment when you don't do the things well. So this is basically how it works, like a baby trying to learn. So it will start from here, it will just go everywhere, hit the walls, get punishment, wouldn't repeat that again. And then eventually, as it gets closer to the target, it gets more reward and more reward. So you just leave it there to train on its own. And this is the power of the reinforcement learning, because you don't have to specifically code corner cases and edge cases. The problem with coding those edge cases manually in a software is that you might not be able to cover them all. You can see some corner cases in certain test cases, but then each home is different, each person is different, and the robot might run into the things that you haven't programmed. So this is very beneficial for those corner cases. You can see reinforcement learning as a game as well. Basically, it's helpful to see it as an agent that is trying to improve its scores. So this is a trained agent, basically, but if you started this fresh to learn on its own, it will just go around and will be punished if it hits the enemies. And every time it hits those dots, it will just get reward. And that's how it learns to improve its actions. And normally in reinforcement learning, you have action space and you have observation space. Action space here is up, left, right, down, right? So and they have limitations in certain corners. And observation space is this image, the location of dots and the location of these enemies. And you can see how that works in robotics as well. You have action space of a robot, that there are wheels, for example, in vacuum cleaners, and you have observation space from sensors and all the cameras and long-range sensors. And you can even add IMU. So the more sensors you give to the robot, it will have more chance to survive more challenging environments. Let's look at one of the classical control or robotics issues, which is navigation. If you want to navigate from point A to B, it's the most famous way to do this is normally using DWA strategy, dynamic window algorithm. I don't want to go into too much details, but you basically have to write code in a classical way to come up with all these trajectories if this is your robot, and you want to avoid these obstacles that your sensors detected, and you want to go to the final point that you can see. Your agent will basically, or your algorithm should come up with all these possibilities and calculate each of them one by one in a horizon of time and see if it results in collision or not. This is how difficult and computationally intensive these algorithms are. But with reinforcement learning, then the paradigm changes. You just let the robot to learn on its own. This is a quick simulation I did. Everything normally happens in simulation in a training session. So you build your robot model, and you see I drop randomized points everywhere in the simulation, and the task of the robot is to navigate to that. But you could complicate this by adding obstacles and punish the robot by every time hitting the obstacles. But basically, this results eventually in a neural network that you could put it in a robot. And based on my experience, you can have that neural network very efficient, and you can compile it, optimize it, and you could sometimes beat the performance of a classical algorithm that you have spent a lot of time optimizing it. So this is what it brings to the table. But it's not that easy. It has its own challenges as well, AI. So one of the challenges is, again, as we were talking, computation. You have to run it on the product. And normally you don't have massive GPUs on these machines. So you need to really, really go and prune your network and reduce the size of it, reduce and optimize the inputs and outputs, and really make it lean so you can run it on the robot. And the updating of it becomes another issue. So you need to have a pipeline in your system to constantly update these models separate from your normal software. Data-driven development is a phase shift that needs to happen in companies if they want to move to AI-driven development. Basically, all the focus in engineering companies, or at least in software teams in classical methods, has normally been on writing the code and writing the behaviors. So you will have different teams writing different behaviors for vision, for, I don't know, obstacle avoidance, and all these things will go into different teams. Now, in data-driven methods, everything changes to building a simulation, building a representative simulated world, and designing all these behaviors in that simulation, and then building a lot of test methods. Testing your models is very, very key in AI-driven development, because AI is normally a black box, and you need to validate it yourself even more because you don't understand what's going there inside the robot. One of the tests, it's interesting, I've been doing. We normally try a lot of different things in a simulator, and sometimes the agent finds very corner cases. Sometimes, you know, you have punishment for the bad behaviors, and sometimes you can design these things in a way that the agent will decide to kill itself by hitting the wall because it can find that the life is so dramatic and painful. So these are things that you sometimes open, you leave your simulator overnight, and then you wake up in the morning, you see the robot constantly running to the wall. What's going on? And you find out, oh, I did give too much punishment for bad movements that it just gives up. A lot of life lessons there as well. So sensor accuracy is another thing. You need to try to model it in your simulator. Sensors are not perfect. Obviously, they have noise, so the simulated sensors should also have noise in there. Limited visibility, robot could go under the cupboard and see nothing. So you need to also create those environments in simulation. Level change, as I said, all the sensors value will change immediately as you go to level change. So you need to have these in your simulator as well. And coverage and going close to the walls and textures on the wall. And these just add more difficulties to your simulations. That was mainly my points I wanted to make. If there is any questions, happy to answer.
I have the microphone. Would anyone like to put their hand up? Really thought-provoking, wasn't it? Do we have anyone who would like to pose a question over here? Front row.
Hi, good evening.
Good evening.
The question I had was, as a company like Dyson, how do you factor in like other companies' innovation as well when you're trying to come up with these new AI models and stuff? Because obviously everyone else is thinking about the same things, trying to do the same things. How much of that factors into your MPI work?
Yeah, it's a very good question. Thank you. So normally in AI, because it translates to the software and as a product, as a result product in the market, you don't normally see tangible difference, or you might see, but you're not certain how to reverse engineer that. So it's normally not that easy to factor in different competitors' behaviors in this scene. So you need to be innovative. So we basically do everything from scratch in the company ourselves, yeah.
Hi, thank you. I thought it was a great presentation.
You're welcome.
I was wondering if Dyson are producing any custom silicon or hardware to accelerate these AI applications.
We have hardware acceleration on the robot, but I can't talk about the silicon details, unfortunately. Yeah.
That's okay. Thank you very much.
Welcome.
Is there anyone else who is pondering a question? Ah, at the back there. Here we go. If you don't mind passing it down.
Hi there.
Hello.
Good evening. Thank you for the presentation.
You're
Just
welcome.
a question, a bit of a wacky one. So do you think that sentience is possible anytime soon, or would that be a far-fetched idea?
Yeah, it turned into a podcast question that we need a few hours probably to talk about. Probably possible in future, because this AI or reinforcement learning at least is very powerful, because you could basically have whatever that's going on in the human brain there, well, with less accuracy or less details, but I don't see why they couldn't achieve a high intelligence by learning in the environment and experimenting. But they always have to be a goal. There should be a goal. Normally, at least in my experience, when you design something, you need to optimize it towards that goal. So what that goal is going to be, that's another topic for conversation, I think. It's a question there as well.
Good evening. It was a fantastic presentation, very thought-provoking and entertaining as
You're
well.
welcome.
My question is about simulations. So does it mean that you had conducted, let's say, a couple of hundreds simulations that covered some specific edges for those simulations, or you just, let's say, build 3 big ones to, have most of the stuff in them?
Very good question. Normally, the scale of simulation runs you do in these sort of problems is over millions. So you need very fast simulation environment. You accelerate the simulations. So for the challenge, I said moving robot from here to there without hitting obstacles, you would try to accelerate and run that 100 times faster than the real world, and you just run it millions and millions, and it will, because first few 100 runs or 1,000 runs are just going to be robot doing nothing, because it's just exploring the environment and learning what the environment means, like a little baby that touches things and looks at the things and trying to make sense of the things. Yeah.
And do you use ROS, robotic operating system? I'm not sure if you can answer those questions. Like, what's frameworks? Can you share a bit?
I can't go into detail of that.
That would be super
Thank you. Yes.
How do you generate the simulations themselves? Because one of the problems that you talked about with traditional algorithms is that you can only create as many edge cases as you yourself can imagine. Are Dyson using kind of environments from real robots that you can bring back into simulation, creating simulations that way, those environments, or are you kind of procedurally generating them? How does that work?
Yeah, procedural generation is the best way, because you want your environment generation code or system to be very flexible, and every part of it should be randomized. If you have walls, you want the thickness of the walls to change. If you have materials, that should change. If you have light shining through your kitchen and one section of your kitchen is too bright, you need to move that light as well. All these things make it more complex to have a good simulation environment. Good question.
How reusable are you've created a product, you've got something that works, you want to create a new one. How much of it can we use? How much do you need to then start from scratch?
Yeah, you could use transform some of these models basically to a new model and fine-tune them if the task is quite similar. It's basically, it's very common now in research, they do it. If you have a object detection model, let's say, that is supposed to detect all the objects, that's a general AI model that detects objects, detects table, chairs. Now you wanna detect certain types of chair, then you can reuse that model and fine-tune it with your customized data set, basically. It's similar for reinforcement learning as well. You can have a model that is trained to deal with certain things. If the task is similar, you could retrain that model as well. Yeah.
Hi. Yeah, excellent
Sorry.
presentation. Really fascinating. One of the things you mentioned was you develop your neural network in simulation, and then you deploy it onto your real hardware.
Yes.
I imagine that's quite an involved step I mean, we can't just take Are you
Yes.
able to take your neural network and just plonk it onto your robot and it works as intended?
No, that's a very good question. That's why I had the challenges of putting the things on the edge or running it on the edge. There's so many layers involved that the network that you trained in, it normally Python or whatever code, a simulation, it works well. You need to do so many layers of testing, evaluation, and change the environment and validate it still in simulation, and then you compile it to different format that can run on the software, on the hardware, and then also validate how much CPU usage, memory usage, and all this is using. Yeah, difficult. Thank you.
Hi, Sid. So I would like to know more about the robot which folds the arranges the plates, cleans everything. I mean, at what point are you in this phase of development?
Yeah, that is responsibility of another team, which I'm not part of it. It's a research team within Dyson, and it's quite confidential, a future-looking program that I can't talk about it other than the videos that are available in YouTube. But the robot stacks plates. So yeah, I encourage you to watch that video. That probably tells more than what I'm allowed to say. So.
Fantastic. Any last thoughts or questions over on the front row?
Hi, I'm really interested in at what point you decide it's good enough. What's your definition of done?
Yes, that's another challenging topic. As I said, in AI-driven development, evaluation is a big thing, and test and realistic test is a big thing. So if you, in your classical methods, you were doing 10 tests and you were happy to release, this time you have to do 100 different tests because, again, you don't understand what is inside the black box. So we try to have all sorts of randomizations in our tests in simulation, because in simulation it's easy to do the test. You could just click a button, 10,000 homes will be generated for you. Then in realistic scenarios, we have fleet of robots that just run all the time and just do these tests for us. So yeah.